So today's video is going to be all about Dijkstra's algorithm and the A-star algorithm. Well, in order to get to understanding the A-star algorithm, we're going to have to take a few steps through traversing a graph, Dijkstra's algorithm, before we then get to the A-star algorithm. So let's start off with what traversing a graph means. Traversing a graph is about moving around a set of nodes. In this case, our nodes would be A, B, C, D, E and F. Obviously this is a more metaphorical representation of a graph, but in real life these could be cities or just different locations, and it's about finding the distance between those different locations. Between nodes you have a cost, so this could be time, this could be distance, it could be pretty much anything as long as it's in relation to the graph. So if you're in our graph, the cost between B and D is 5, or you could say the cost between B and E is 8, and so on. Imagine that all these nodes could be cities, for example, and you're a delivery driver. You can see that it could be really useful to find out the distance between these different cities. But then you could also start to think, well, you might need an algorithm or a way of thinking that could find you the shortest distance between the cities. So that as a delivery driver, you can deliver parcels in the quickest time and make the most amount of money. And this is where Dijkstra's algorithm and the A-star algorithm come into play, because it's their job to find the shortest distance or the shortest cost between nodes. So let's go on to talk about Dijkstra's algorithm. So I'm now going to give you a walkthrough of how Dijkstra's algorithm works. And for Dijkstra's algorithm to work, we're going to need a starting node and a goal node. So we're wanting to get from A to F. So to start off with, we're going to assign some tentative values to our nodes. A has a tentative value of 0, because to go from A to A, you're not actually going anywhere. So it has a cost of 0. And let's imagine we're stood at A. We can't really figure out any of the other distances to B, C, D or E or F. So these are all infinity, because we have no idea what their cost is. I must also point out as a side note that all the nodes in the graph have been added to a queue that they need to be dealt with. And this is being calculated by using a breadth first search, which is kind of added them in an order going A, C, B, E, D, F. So that we're making sure we're going to look at all the nodes in the graph. So we're at A. Let's then go to C. C's tentative value can be replaced as 2, because we can see that from A to C the cost is 2. B then gets replaced as 4. And we can now take the node A out of the queue, because we've found all possible exits out of A and the tentative costs. We'll then go to C, because it's got the lowest tentative cost, which is still in the queue, and we'll look at its neighbours, which are B and E. You can see that to go from C to B it's only 1, and this gets added to the tentative value, which means B's tentative value now becomes 3. So already we're starting to find quicker paths around the graph, because we found it's quicker to go ACB rather than AB. E's value also becomes 12, because C's tentative value gets added to the cost. And we can now take C out of the queue, because we found all available exits. We then go to B. D becomes 8, and E becomes 11. And B can be taken out of the queue. We then go to D, and we're getting quite excited now, because we think that we've nearly found the shortest path, because F is 14. So some people might stop there, but Dijkstra's algorithm will not, because that may not be the most efficient path. And if you stop to think about it, it probably isn't, because we've not looked at all of D's neighbours, because E could well be a shorter path. And if we look here already, 8 plus 2 is actually 10, so it is getting reduced. And then D is taken out of the queue. And then we can actually see that 10 plus 3 is 13. So then rather than giving up the moment that we'd found a distance or a cost to F, we made sure that we looked at all the available nodes before making that final decision. So we can now see that the fastest path to F was going A, C, B, E, F. And that's how Dijkstra's algorithm works. Dijkstra's algorithm is all well and good for graphs such as the one I just showed you, but it can have its problems, and this is why the A-star algorithm was brought into play. Because let's imagine we're at B, and we were wanting to get to E. Dijkstra's algorithm will actually go all the way up to A, and then it will check all this out. It's got absolutely no sense of direction. It's like a bit of a lost person, really. So it'll just wander around until it's found the best path. Admittedly, for a computer, it will do it very fast. But that could be made faster if, when we're at B, our little person that's wandering around knows that E's over here. So instantly, it will be able to scrap A out of the equation because it knows that that's just not going to work at all. And this really is what brings us in to talk about the A-star algorithm and why it's much more efficient. So I'm now going to give you a run through of how the A-star algorithm works. And it's exactly the same graph as before. And you'll probably notice that these nodes have little numbers on them, such as 6 and 3. These are our heuristic values, and these are what are individual and unique to the A-star algorithm. They're approximations of a distance from the goal to that node. So you can see that D is closer to F, so it's got a lower heuristic value. Our heuristic values are actually based on inches on a smaller drawing of this graph, if you were just wondering. We'll do a walkthrough of the A-star algorithm, and it'll probably make more sense why these heuristic values are there and how they help the graph know which direction it's roughly going in, as I was just talking about earlier. So it starts exactly the same as Dijkstra's algorithm, and we're just going to apply these tentative values. Once we've applied it to F. But now this is when it starts to become the A-star algorithm, because we can now apply an A-star score to node A. The A-star score is the tentative value plus the heuristic value. So for A, that's going to be 7. And we can now start to look at the neighbours of A, which are B and C. C has a smaller cost, so I'm going to look at that one next. And the same as in Dijkstra's algorithm, we're just going to swap this for a 2. But then you will also see that its heuristic value, or its A-star score, is 8, because it's 2 plus the 6 on the C. And we're now going to go to the B, which has got a tentative value of 4, but an A-star score of 10, because it's 4 plus 6. And now we can take A out of the queue, as you would in the Dijkstra's algorithm. But now, instead of in Dijkstra's, where you would choose the lowest tentative value, you're going to use the lowest A-star score, which in this case is C with 8. So you can see now, as you're going through the graph, the lower the A-star score, it means the lower the heuristic value was. So that means the closer it is to the goal. So you can sort of see how it's managing to guide the graph traversal in the correct direction. So we'll now go to C, and we can look up to B, and we'll see that B's value, tentative value, can be swapped to a 3, which now means its A-star score can become 9, because it's a tentative value plus the heuristic value. E then becomes 2 plus 10, which is 12, plus the 3 to make an A-star score of 15. And C has been worked. Now, we just got the lower A-star score. That's B, so we'll select B. B to D, so D's tentative value is 3 plus 5, which is 8. And then its A-star score is 8 plus 3, being 11. And we'll also look at the other neighbours of B, being E. So can we get to E any quicker from B? Which would be 3 plus 8, which is 11. So yes, we can. So we'll swap that score out for an 11. And 11 plus 3 is actually 14. So that A-star score changes. and B can be taken out of the queue. We'll now look at the A-star scores, and D is smaller, so that means that is closer to F. So we're going to go to D. And as with Dijkstra's, we'll notice that we are very close to F now. So it's 8 plus 6, so it has a cost of 14. And because it has a heuristic value of 0, that means the A-star score is 14, which is nice because when you get to the goal, the A-star score is actually the same as the cost. So you know you've definitely got there. However, we need to finish looking at the rest of the neighbours of D, because we can see that the tentative value to E from D is actually 10, which then updates its A-star score to 13. Now you'll notice that E actually has a lower A-star score than F. So this means it's got a higher priority even than the goal node. So we need to make sure that we go to E to find out why it's got a lower A-star score. So let's work out the tentative value first, which is 13. Which then updates the A-star score of F to 13. So by using this heuristic value, we figured out that there was a quicker path to F. But it also means if you think about the graph I was talking about earlier, if A, which was over on this side, that would have a massive heuristic value opposed to the ones that are on the right-hand side. So the traversal would instantly move, or the algorithm would instantly move to the right-hand side, getting there quicker. So that's how the A-star algorithm works.